Today we're going to focus on centripetal accelerations. Now, a centripetal acceleration is an acceleration in which the object's speed doesn't change, but its direction does. And we're going to focus on a specific type of acceleration. And the word centripetal refers to it. It's talking about an acceleration where an object's traveling in a strictly circular path. Now, I have to say that because you can have paths that are certainly not circular, that are curved. But under those circumstances, if the curvature is changing a lot, then probably the way in which your acceleration is operating is also changing a lot. So we're going to focus on things in which our situation stays relatively the same. For this case, let's consider what we saw. I mean, we saw something I think pretty clear, but maybe you feel differently about it. So I'm going to try and draw it out as much as I can. So from the top, we had a stopper that was connected by a string to a little thing I was holding. So from the side, it would look maybe more like this. I have my little handle. That's not what I meant to do. This is what I wanted to do. There's my handle. There's a string. Went into the handle like that. And then there was a weight down here at the bottom. But the object was clearly traveling in a circle. There. Is that decent pictures of what we saw? From the top and from the side? Now, if you think for a moment what's happening, at this instant the stopper had a velocity in that direction. Right? That's the direction the stopper was going. But a moment later, the stopper's located over here, and the string has shifted to be over here, but now the velocity is this direction. Now the velocity's magnitude, the speed, never changed, but the direction changed. Now the only way that could happen is if there was no component of acceleration in the direction of motion. If there was a component of acceleration in the direction of motion, then the object's speed would have increased or decreased. Right? That's the way acceleration works. If you have an acceleration in the direction of motion, your object's either going to go faster or go slower. So the only way we can have an acceleration in this example that isn't in the direction of motion is if the acceleration was perpendicular to the velocity, which means towards the center. So in this case, in any case where an object's changing direction, there has to be an acceleration that is perpendicular to the velocity. That's what this word means. The left side of that word, center. The right side of that part is seeking or looking. So a centripetal acceleration is one that is pointed towards the center, always. So this acceleration is changing direction all the time, but it's always pointed towards the center. Now, the size of this acceleration has to be calculated a little differently. We're no longer talking about dv dt or delta v over delta t. Right? That's not going to work for us because the object's speed isn't changing. So we have to have a different way of calculating it because the speed is staying constant. So we put the little c there to remind us that this is a centripetal acceleration, and we calculated it as v squared over r, where v represents the speed and the r represents the radius of curvature. That's how you calculate a centripetal acceleration. Now, this doesn't change hardly any of what we talked about when it comes to forces. In order for something to travel in a circular path, there must be an unbalanced force that causes this change in motion. When you watch the stopper, it wasn't a new force that was acting on the stopper, it was tension. There was a string attached to the stopper, and it was the string that caused the stopper's motion to change. In all circumstances in which an object is going to change direction, one of the forces we've already talked about has to cause that change in motion. So when we talk about force problems from now on, it's not just about whether an object speeds up or slows down, it's about any situation in which an object could change direction. Let's consider an example of what this would look like in practice. You guys have seen the intersection of Sheldon and Citrus Park, right? Now, you may not know this because you've probably never pulled it up on Google Maps or any other satellite image, but the intersection is awful. It's just an awful intersection. It was awful before they added the other part to Citrus Park, and now that they've added the extension to Citrus Park Boulevard, it's just gotten worse. Part of the reason is because the intersection is busy, one of the busier intersections in Tampa, and there's a lot of pressure, but it's also not a 90-degree turn. It's slightly more than 90 degrees to make that turn, and a lot of people who drive are incapable of making that turn. If you look closely at what happens, people try to beat that yellow light, and when they do so, especially now that there's more than one left turn lane, it causes accidents there frequently because you reach a point where your car can't turn any faster. There's a limit to how fast a car can turn. And it's based on physical properties of the road and the tires in the car, and not things you can easily control. Of course, first thing people do is they either widen their turn, which causes a wreck because there's a person next to you, or they try to slam on their brakes while they're turning, and that usually ends badly too, as the back end of the car tends to spin out from behind them. That intersection's not great. You should be careful there. Let's talk about a more straightforward intersection, though, one that we can speak to with a little bit more simplicity. Let's consider a standard right angle turn where you're going to be coming from this lane and heading to this lane, because you guys are aware you're supposed to go from the leftmost lane to the leftmost lane when you make a left-hand turn. You're not supposed to be opening up your turn and going into the right-hand lane. You do it anyways, but there are rules, and we're supposed to be following them. We're a society. Let's say your car is traveling at a 10 meter per second speed, roughly 20, 21 miles an hour, which is pretty fast to take a turn. And let's say that the radius of curvature for this turn is 30 meters. Intersections are designed to accommodate turns at a certain speed. What is the minimum coefficient of friction to make the turn? Now, in order to solve this problem, I think you probably understand that this is a force problem, right? That's where the coefficient of friction shows up. It shows up in force equations. So we are likely going to have to analyze this as a force problem. To do this problem, I want to remind you of a couple things. First, what kind of friction do you think we're talking about here? Kinetic friction or static friction? A lot of people say kinetic here because the car is moving, but are your tires sliding with respect to the roadway? I mean, is that what you would like? Do you want to be sliding along the roadway? Or would you like your tires to stay in firm contact with the road? It's static for sure. Yeah, if you're having to deal with kinetic friction in your tires, you are probably having a bad day, okay? Because you'll be sliding then. So no, we want our tires to be in static contact with the ground and not sliding with respect to the ground. Most of your cars have come with anti-lock brakes and other mechanisms to prevent you from sliding with respect to the ground. So if you ever are sliding with respect to the ground, like I said, you have broken friction and you're now sliding. That's bad news. You have no steering. You have no ability to control the car really dynamically unless you really understand how to drift. And that's probably not most of you in the room unless it's a video game. So there might be a few of you who have played along with that. Not me, no thank you. But you guys, Keep that to the track, not on real roads. So consider the forces acting on the car. I'm going to draw the car from the back. It's not going to look like a car because I'm terrible. It's a hamburger. Yeah. So you're driving your hamburger down the street. What forces are acting on the car while it's making the turn? Gravity, certainly. What else? Normal force. What else? Go ahead.
Wouldn't the car's inertia push it to the right if you're making a turn to the left?
Well, the car will have inertia, but inertia is not a force. So you're right. When you're in the car and you make a left turn, it feels like everything in the car is going to the right side of the car, you included, because you want to travel in a straight line. In fact, we'll talk about that in just a second. So actually, might as well talk about it now. I mean, if you consider what you call inertia, I'll remind you, inertia is an object's resistance to acceleration. That's what inertia is. So things want to stay moving in the same straight line path they were moving along before. So anybody play that game when you were younger, or maybe you play it now if you're in the back seat, and a couple of you in a row in the back seat, like if you had like a little brother and another little brother or something like that, and when you make the turn, you try to slam the kid that's on the one side into the door. How many of you have played this game before or have had it played on you? Okay. Certainly, if you've played the game before, you understand how it works. The kid that's sitting on the left side, well, those right turns, he gets hit into the door. And the kid that's sitting on the right side, those left turns, he gets hit into the door. That's the way those games are played. And it's simple because you have the inertia working with you under this circumstance. So consider the kid here during the turn. When the car begins to make the turn, the kid wants to keep going in his same straight line path. So he's now feeling like he wants to be here. So things and elements in the car have to push on him to get him to travel in a circular path too. That's why if you have something sitting on the dash of your car, it may make it to a different location. It might just slide across the front of your car. Why? Because there needs to be a force to keep it traveling in a circle. And if there wasn't anything there, if the friction wasn't strong enough, it just flies across the car. It's certainly due to inertia, but inertia isn't throwing things onto the right side of the car. Inertia means that the things want to keep going in a straight line, and the car is moving underneath them. So that's what you feel when you feel inertia. But something has to cause you to move with the car. Some force has to act on you for you to move with the car. The only thing that doesn't follow these rules are balloons. Anybody ever have balloons in the car? They seem to have a mind of their own, don't they? Well, they don't have as much of a mind of their own as you might think. If you have helium balloons in your car, well, helium is lighter than air. So air has inertia. When you speed up from a stop, like a stoplight, and you speed up, the air in the car goes to the back of the car because the car is going forwards. The air stays in place. So when you go forwards and the air stays in place, it pushes the helium balloons to the front of the car with you. They accelerate forwards because the heavier air stays in the back. When you stop, the reverse happens. The balloons go to the back of the car. Because when you stop, all the air seems to be stuck in the front because it has inertia, displaces the balloons to the back. Turns will do all the same thing. You make a left turn, the air wants to go in a straight line, so all that air tends to be on the right side of the car, the balloons go to the left. Balloons actually move in the direction of the acceleration in the car. In fact, you can make a simple accelerometer that would tell you what direction your car is accelerating. All it is a balloon on a string. Just follow the balloon. The balloon is going to lean in whatever direction the car is accelerating because it's being displaced by the heavier air. Now, back to our problem here. What direction must the friction be pushing on the car in order for it to make the turn? Yeah, you only have two choices for friction here, don't you? Right? It's going to have to be perpendicular to the normal force. So if you want your car to turn to the left, there has to be a force that pushes it to the left. It's that simple. Now we know this frictional force is going to change direction. It's always going to point towards the center of your direction of motion. But this has to be the force that acts on the car to cause the car to change direction. There has to be an unbalanced force. Remember, all of these problems that involve circular motion are going to have to be Newton's second law problems because there's an acceleration involved. Now I have to choose a coordinate system. I think the best coordinate system is the one that's lined up with an acceleration. You will always benefit from making sure that the positive direction is the direction of your acceleration. I would strongly encourage it, especially for these problems. So I have an unbalanced force in the x direction. That's going to cause my centripetal acceleration. And I have a balanced force in the y direction. Because like always, whatever direction I've chosen to be my direction of my acceleration, my other one should be net force of 0. And from here, we just work the problem like we would any other net force problem. I have one force in the x direction. That's got to equal to MAC. And I have two forces in the y direction. They have to sum to be 0. Now, the force concept model still does the same thing. It produces two relationships that might be able to be used to solve your problem. But you have to decide if there's ample ways to use them. Now, getting away from the problem and just looking at what we have used the force concept model to do, we have two relationships now. Do either of those have the coefficient of friction in them? Where?
You can replace the force in the coefficient of friction with the force in like the equation.
Okay, so we're going to bring this equation into it, I think is what you're trying to say to me. That makes sense? All right. This is an inequality. So because it's an inequality, I'm going to substitute into the inequality, as opposed to doing the reverse, which is to do a substitution out of the inequality. So I'm going to plug this in here, and it looks like that in there. That look good to you guys? So I'll get MAC for the frictional force, and I'll have mu s mg for the normal force. A couple of substitutions at once, but these work together okay. Any trouble with this? All right. AC, we're going to replace that, right? We know something to replace it with because we have information about how the car is trying to make the turn. 10 meters per second, 30 meter turn. So I'm going to replace AC with v squared over r because we're dealing with a centripetal acceleration problem. And that's going to be less than or equal to mu s mg. Now I see a clear way to get to our answer. Do you? We're trying to figure out what the minimum coefficient of friction is. I never gave you the mass of the car, and it looks like it won't matter. All cars kind of obey the same kind of principles here. If I solve this for mu s, I get v squared over g times r. And look, it's an inequality, which is what I want. I want to know I'm at a minimum or a maximum. The problem asks for the minimum coefficient of friction. That would be necessary to make sure the car could safely make it through the turn. Looks like we can figure it out here, and it says that mu s has to be greater than or equal to this value, so this is going to give us a minimum. V squared was 10, right? 10 squared over g, which is 10, over r, which is 30. Looks like as long as I have a coefficient of friction of 0.3 or higher, I should be able to successfully make the turn. And you certainly will have that. So if you guys have done or at least started working on your coefficient of friction lab, you know that the coefficient of friction for the shoe is pretty high. It's well over 0.3, which is why, tires on asphalt probably pretty high too. If done right, tires on asphalt are usually somewhere around 0.6 or 0.7. You want to make them nice and sticky relative to the ground. Now, we live in Florida. First thing that happens when it starts to rain here, coefficient of friction on all your road surfaces goes down. This is why they tell you to slow down when it's raining and making turns and trying to stop. Because as soon as it starts to rain, especially when it first starts to rain, you guys learned that too, right? That the first instance of rain is the worst when it's just drizzling out a little bit, because all the oil that's on the road now is brought up to the road surface, making it slicker than it will be after it's been raining for a long time. After it's been raining for a long time, most of those oils get washed away and the coefficient goes back up a little bit. But that first coating of water on the ground is the most dangerous when it first starts to rain out. That's where you have to be extra cautious. So when you're dealing with Florida, those are some things. How about another one? I got another one, all right? What if you're driving and there's a dip in the road? Roller coasters do this all the time. Have a place at the bottom of a turn where there's a dip. Same idea here. Let's say you're driving and you find a dip in the road and you make it to the bottom of the dip. Let's say there's a radius of curvature of the dip that is 40 meters. And let's say you're traveling at a constant speed of 20 meters per second. How much heavier do you feel at the bottom of the dip? Let's say you maintain your speed of 20 meters per second as you're going through the dip. Does this constitute a uniform circular motion problem? Do you see the car traveling in a circular path? I think so. It's not turning or anything, but that's clearly a circular path. A lot of people in first period didn't see this as a circular path, but if it's not a circular path, and you say the forces are balanced here, say normal and weight, if those are the only two forces and they're balanced, then you are going to go in a straight line. That's probably unlikely what you're attempting to do. The only way you can make it out of here is if there's an upward force that is greater than a downward force. There has to be something that causes you to have a change in direction. So, in a problem like this, there must be something acting on the car that's greater than the weight of the car. The weight of the car isn't going to change, is it? The weight of the car is going to stay the same. So, I'll remind you that the normal force is a responding force. It will respond to the conditions required to maintain the motion of the car. So the road will push up more on the car at the bottom to ensure that there can be a change in direction for the car. This is why you feel that. You ever get into the bottom of a roller coaster and you feel that pressing into the chair kind of thing happening? That's not you pressing into the chair. That's your inertia making you want to go in a straight line, and the car's pressing up on you to get you to change direction. And that's what happens here. So I'm going to make the upwards direction the direction of my positive coordinate system. So coordinate system like this. I'll make this the positive y direction. I don't have to worry about the x direction. And I'm going to say that the net force equals MAC. Now I asked you to figure out how much heavier you feel. So let's see what this looks like. There are two forces acting on you, the normal and weight. And that has to equal MAC. So there's your weight plus the amount extra required because you're traveling in a circular path. Now, obviously, if you're paying attention, you know we're going to substitute in v squared over r. So if you're designing the roller coaster and you want to ramp up what people feel at the bottom, you do so by making this part change. You know how they refer to like the g-forces you experience in most roller coasters? Most of the g-forces you experience in a roller coaster aren't because of how fast you're going, but how tight the turn is. That's the easiest way to ramp up the acceleration. They don't necessarily want you going that fast. So they usually just make tight corners. That's what roller coasters are all about. You're probably never traveling more than 30 miles an hour on most of your roller coasters. here is to say you want to feel twice your weight or 3 times your weight. How fast must you be going? How tight must the turn be? That's this problem all day long. I didn't give you the mass, so we really have nothing to go by, but I did give you this and this, which means that in the part that's here, 20 squared divided by 40 is going to be 10, right? And since G is 10, this is the perfect conditions for you to feel twice your weight at the bottom, because all of this is going to be the same value as G. So if you want to feel 2 G's, this is what you would have to set up. You'd feel twice your body weight. Of course, and the old Gwazi used to do this really well. The new Gwazi does it okay. Let's say that you're driving your car and you come to a hill. What's the fastest you can travel without jumping your car? And I know you're probably asking, I don't understand, Mr. Shelton. Well, let's reason it out. This looks like a circular path, doesn't it? The radius of curvature here, let's say it's 40 meters again. What forces are acting on the car when you're at the top of this hill? Still gravity. And what else? What's that? The normal force in the ground. But what direction must the unbalanced force be for you to make this successful turn? Right? You're turning by going across the top. Wouldn't the downward force have to be greater than the upward force? Well, the only thing providing an upward force is the normal force. Can a normal force grab onto you and pull you downwards? No. So there must be an unbalanced force in order for you to make it over the top of this hill. These are the only 2 forces acting on you, so the normal force must reduce in order for the weight to pull you downwards. And this is exactly how you feel on this ride. You feel like you're coming out of your seat. That's because the vehicle you're in is being pulled downwards and you want to go in a straight line. So it feels like the car gets pulled out from under you. I'm going to make downwards the positive direction, because that's the direction of the acceleration. So I'll make that positive y. Again, net force equals MAC. There are 2 forces acting here, but I'm going to make downwards positive. So this is weight minus normal force equals mv squared over r. Now, as you look at this, do you realize quite clearly if V is 0, then weight just equals normal force? Is that pretty clear? Now, if V is anything else, the weight can't change, so the normal force must start to become smaller and smaller and smaller. What's the smallest the normal force can become? 0. Yeah, because it can't be negative. It can't pull you downwards. So the smallest it can become, and that makes for your maximum speed, is when the normal force is 0. All right, folks. I will